Hi folks, I'm Karthikeyan Chandrasekhar, working as an assistant professor in the Department of Electronics and Communication Engineering from R.M.K College of Engineering and Technology. Today in this session, we will be discussing about analog to digital and digital to analog converters from Unit 3 and linear integrated circuits. So the course objective of the Unit 3 is to provide the outline for the working principle of analog to digital converters and digital to analog converters. Digital to analog converters, the first, the input will be my binary input, which we used to call as either zeros or ones, which is commonly referred as digital signal, is being obtained as an output in the form of waveforms and which we referred as analog signal. So my input will be the binary numbers either 0 or 1 and the output is analog waveform. Here we have three types of DAC. The first one, weighted resistor DAC, second one R to R DAC, and the third one we will be having inverted R to R ladder DAC. So today we will be discussing about weighted resistor and R to R followed by inverted R. So specifically weighted resistor, we just look into it. The first one, weighted resistor DAC. So in the unit 1, we would have been constructed inverting operation amplifier. So everyone draw the inverting operation amplifier where in the negative terminal of my op-amp, the output, the voltage has been provided, input voltage is provided, and we have the negative feedback resistance from my output is connected to my input, a resistance is connected, and the non-inverting terminal. So usually we never prefer here. So the positive terminal of an inverting amplifier is being grounded. So here weighted resistor, it means in each resistance we are going to provide some weight. So the first resistance, usually we will be drawing a resistor and denoted as capital R. Weighted means 2 power 1 for the respective resistance and 2 power 2 is provided as a weight the second resistance, and for 2 power 3 for the third resistance, like 2 power 4 for the fourth resistance. Like that we will be providing an weight for the resistance, and the current that flows across each resistance we call it as I1, I2, I3 till IN respectively. And there is a switches we call it as SPDT, single pole double throw switch. There will be only one pole, single pole, but double throw. It might be connected to the ground, which we logically consider as 0. If it is connected to the negative reference voltage, which we could see in D3, which we'll call it as logically 1. So single pole double throw switches. So D1 starts from the most significant bit and Dn where it ends we call it as least significant bit. And this is the overall construction of the circuit diagram. I just repeat, so here we will be constructing from unit 1 inverting amplifier with the negative feedback resistance. Since the type is weighted resistor, so in each resistance we have provide some weight with 2 power base as a polynomial of 1, 2, 3 respectively. And there is a SPDT single pole double throw switch. D1 starts from the MSB and Dn that ends in LSB. If any other switch is connected to the ground, it is binary input as 0. If it is connected to the negative reference voltage, it is considered as logically 1. If we just look into the analysis, so my output current is equal to sum of all the currents in each resistance. We know from Ohm's law, V is equal to I into R. So it is in the format of I is equal to V by R. I1 is equal to VR reference voltage divided by 2R. Since it is a negative reference voltage, we are supposed to put minus here, and I2 is equal to minus VR divided by 2 power 2R into D2 plus I3 is equal to minus VR divided by 2 power 3R into D3, like IN is equal to minus VR divided by 2 power NR into DN. So we are taking minus VR divided by R as common. We will be getting D1 divided by 2 plus D2 divided by 2 power 2 plus D3 divided by 2 power 3 plus Dn divided by 2 power n. When the denominator goes to the numerator, we will be having D1 into 2 power minus 1 plus D2 into 2 power minus 2 plus Dn into 2 power minus n into minus Vr divided by R. So this is the output current. The output voltage is equal to, so from the circuit diagram, V is not is equal to minus I naught into RF, because the arrow bar of my output current is in the closed loop, points towards the negative terminal of op amp. So hence V naught is equal to minus I naught into RF. Substitute the value of I naught. So minus into minus, it provides us plus. So substitute the value of I naught into RF. So this is the final output voltage of weighted resistor DAC. So the transfer characteristics of DAC. So the provided input voltage is digital, that starts with the decimal number of 0 to 7, which points to the 3-bit DAC in terms of digital. And then we will be having an analog output voltage. Since it is a 3-bit DAC, so the maximum value is 2 power 3 is equal to 8. So VR by 8, 2 VR by 8, subsequently till 7 VR divided by 8. So in the introduction part of ADC and DAC, so after smoothing filter, we will be obtaining a staircase output, and this is about the transfer characteristic of DAC. Next, the ultimate drawback of weighted resistor DAC is if the number of bits is increased in the conversion, like 3-bit DAC we have discussed, if we go for 10-bit DAC or 15-bit or 20-bit DAC, absolutely the resistor value will also increase, because of which there will be more power dissipation. In order to avoid these critique, we will be moving to R2R type DAC. Thank you.